What's going on, everyone? Embedded Monkey here again. And today is Embedded Adventure Day 16, where I'm as a complete beginner trying to learn embedded systems, IoT, all that stuff, and doing this with ESP32 microcontroller. Yep. By the way, Cap is back again. Yep. I haven't forgot about the cap. I just removed it in previous series. I don't know why. And in previous series, we actually started to learn ADC and DAC, like how they internally work. We haven't programmed anything. Well, we maybe program something today. But basically, ADC and DAC are just GPIO related, and we have already programmed a lot of GPIO stuff. At least for output, yep. So, at least for that thing, for LED, yep. So when I'm gonna buy some input peripherals like buttons, maybe sensors, I hope I will do it, well, maybe a little closer to New Year. By the way, New Year in 2 weeks. Oh my god. Okay. And then I'll learn how they work. So how the ADC work, not DAC, right? Okay. But we started in a completely different order. In previous series, we actually learned how the ADC works, yep, and not how the DAC works. So today probably I'm gonna continue just exploring the DAC topic with ChatGPT. I guess this video wouldn't be very long because as I mentioned in previous series, I just have lots of studying now. So probably today's video will be a little shorter than average, but nevertheless, okay, so let's jump into it. First of all, we learned how the ADC works. Basically, we have some analog input signal. Then, as we switch the we close the switch every amount of milliseconds or nanoseconds. This analog input signal charges the capacitor, and then when we switch it back, the capacitor goes here. This is a comparator, and it compares against. By the way, this is not the correct schema, I guess. Yeah, that is the one correct. So we got the input voltage, and here we got this. Yep, the ADC uses the DAC internally, so we definitely need to know how the DAC works. Yep, and then I'll finally have like a big picture how it works. So basically, it just interprets the voltage from the counter. So initially it is just zero, plain zero, so it just outputs a zero here. The comparator goes either high voltage or low voltage. So basically, if this voltage is more than this, it'll output 1. If it's less, it will output 0. So initially it will output 1, counter will count, and then we'll get some increment in voltage in VDAC. Yep, and this process will continue until this thing outputs 0. So when it outputs 0, control unit loads the counter value to the latch. This is basically a binary interpretation of our input voltage. Yep, and the DAC is supposed to do different thing, but how? How does it do that? By the way, I probably can actually send him this picture. Yep, I have a circuit diagram for ADC, can you explain how DAC works now? I hope I didn't run out of tokens. Yep. What you have here is a counter type diagram ramp ADC, and understanding the DAC inside it is the key to understanding the whole converter. I'll explain how the DAC works and how it interacts the rest. Okay. DAC job is in this ADC. And what analog voltage does. Yep, yeah. Conceptual view of the DAC. DAC is the inverse of ADC. So yeah, it converts binary number to an analog voltage. Yep. If the DAC is AND bit reference voltage V reference, then this is the formula, yep. So we get the digital value, then we divide it by the maximum number that can fit in the AND bit. Well, basically the maximum number that can be represented by AND bits. Then we apply this to V reference. That's actually interesting why this formula actually is correct. Like, well, okay, say we have like 4-bit DAC, yep. And we have, for example, oh, I got it. So the V reference is basically the maximum voltage that can be output from DAC. Yep. And this is basically the percentage. So if we reach maximum value, so this value is basically 2 to the power of 4 minus 1, so it's 15. And if we divide it by 2 to the power of 4 minus 1, we'll get 1. So V reference is actually 5 volts. And all of these are just like incremental, I don't know, like percentages of V reference. Yeah, of something like that. So, okay. How a DAC is built electronically, Corridian. Okay. The most common resistor ladder, R-2R DAC. This is almost certainly what's conceptually inside your block. R-2R ladder DAC. Use only 2 resistor values, R and 2R. Each digital bit controls a switch. Switch connects either VREF or ground. Okay, let's just Google the normal R-2R DAC. Damn, I definitely should study electronics a little bit more. because embedded world is full of electronics actually. It's not just like about, you know, I heard many YouTubers said that embedded systems is just all about writing to some magical addresses and to reading from them. So eventually you just write to some address inside your microcontroller and then you get some result. But probably that's only partially true. Actually, there are a lot more things to actually learn. For example, this. Yep. I currently don't really understand. Well, of course I know what is a resistor is. Yep. So it give you resistance. Of course I know that voltage is equal, that current is equal to that voltage divided by resistance. Yep. But I haven't practiced it, so that's quite hard to understand. But we'll try. We'll try. At least we'll try. So here are the bits that goes to the DAC, right? If we close the switch, so okay, if all switches are closed, what do we get? What do we get here in V0? Like, let's just go to the site. What the? Disable ad blocker, bro. No. No way. I will not disable ad blocker. Sorry. I'm not interested in this. Let's go here. Okay, so why we use R-2R ladder DA converter? As we know, the vital problem in the weighted register DA converter is use of huge range of different resistance. Suppose we have to design 8-bit weighted resistor DA converter, then we need the resistance value of 2 to the power of 0 on R plus 2 to the power of 1 to R plus etc etc etc. So like this voltage gets 2 to the power of 3 more 2 to the power of 3 times more resistance than this voltage. Or am I wrong? So the largest resistor corresponding to bit B8 is, oh yeah, it's basically written that what I just said. Yep. Case of R-2R ladder DA converter. Okay. Of only 2 value, R and 2R are used. Now and below, see the simple ladder network. Sorry. Okay, so we see it. Binary ladder network for DA conversion. Working processing ladder circuit, the output voltage is also weighted sum of the corresponding digital input. Let's take an example to understand how it works. 4-bit ladder. So we take an example to convert analog signal corresponds to of 1000 digital bit. Okay. For 1000 bit we can see only MSB got 1, the rest all bits got 0. See the below picture and see how it works if it got 1000. Okay. So, as I can see, the most significant bit got some voltage, and other ones are just connected to the ground, which basically logical because they're 0. Yeah. Firstly, at node 1, resistor 2R connected in B4 parallel with the resistor 2R. Those two are parallel resistors, make equivalent resistor of R shown in below diagram. So you mean like, oh, he means like this two are connected in parallel? Well, yeah, they can be like, yeah, they definitely connected in parallel. Okay, and we have the equivalent of R here. So I guess the same thing happens for B3. Since, well, one moment. Like first let node 1 resistor 2R connect in B4. Resistor 2R in this. Okay. Secondly, for N2, same thing happens for B3 series with 2R and parallel with R plus R resistors. It will also make equivalent resistor R at N3. Okay, okay. The same purpose we got equivalent of R resistor at N4. Okay. Then 4, if we calculate the output analog equivalent voltage, then we will get the VR divided by 2. So basically it works a little bit upside down in terms of if you input the value of like 4-bit value, yep, you input a 4-bit value. So the values that have, so the bit that is 1, and in position, let's go and make some paint drawing. Some paint drawing as usual. What the? Okay. Some paint drawing. So, say we have like a 4-bit number, yep. 4-bit number. Well, actually, some bit number. And we got the bit in the position I, yep. So, if it's 0, then it's 0. If it's 1, then we have V plus, so the V will be more like Vref divided by what? By, well, if the maximum is divided by 2, or am I getting something wrong? Probably getting something wrong. One moment. So we got the VR divided by 2. When we had like the most significant bit equal to 1. Yep. Well, is it like a divider or something like that? Probably it's like a one moment. Just curious, I've heard of it. Divider circuit. Well, seems like a proper voltage divider. Yeah, but it's very I'm very familiar with it. Well, at least I heard about it. Dividers. So the output is 2 divided by R1 plus R2. So I guess firstly I have to understand how the voltage divider works. Then I can actually see how the DAC works. No, let's go here. Just to read a little more about it. Voltage divider circuit is a very common circuit that takes a higher voltage and converts it to a lower one by using a pair of resistors. The output voltage is based on Ohm's law and is shown below. So this is the output. So the output voltage from here is equal to the output voltage from here, or what? Got the Vs on like R2 divided by not convincing. What about here? I just want to know where, like, how this formula, how we get this formula, like, why is it so? Because, well, we can actually logically think. Say we have well, actually, we probably can't really distinguish, like, the voltage power in terms of, like, we can't really draw the line here and say, hey, this one is start, this one is finish, but well, if we do so, then we'll get the, here's the resistor 1, here's the resistor 2, right? And basically we take V out voltage either from here, V out, yep, or we take it from the beginning. okay, if we take it from here, this is R1, this is R2. Then we have this fancy formula for parallel resistors. As far as I know, we can actually add them up, and this will basically mean that R is equal to R2 plus R1. Yeah, it basically means that we will have R1 multiplied by R2 divided by R1 plus R2. So this actually seems similar to this formula, but not really, because we don't have R1 here. We have just input voltage. Yep. We only have the input voltage here. By the way, as we all know, there is a Ohm's law. I hope I pronounced it correctly in English. Which basically tells us that the current power is equal to voltage divided by resistance. And by the way, I saw that in many English sources the voltage is the V letter. Well, we usually used to use the U letter. But okay, let's just switch to V for simplicity. Let's just switch to V. So we'll know that there is the law like this. And if we want to calculate the current power here, yep, what we need to do, we need to divide the voltage, which is basically V input. We have to divide it by the resistance, so by R1. Yep, by R1. Okay. This is basically the current value here. Yep. And to find the voltage, yep. So from this formula we want to find the voltage. The voltage is basically current multiplied by resistance. So basically, if we want to find V out from here, we should, by the way, let's call it like I in. Yep. We should multiply I in by the, let's call it, I don't know, R2D2. Yay. So we multiply the input current by this like whole resistance of this circuit, and we get what? We get Vi in divided by R1. Then we multiply it with the R1, R2, R1 plus R2. These guys cancel out. We get the V input multiplied by the R2 divided by R1 plus R2. Boom. Yep. I just like to actually prove some formulas. Yep. So yeah, that was correct, as you can see. The formula is actually correct. That's only part of thing. We have to continue to actually understand how it works. Well, basically I understand how it works. So the output voltage will be definitely less than V input voltage. And it will be less in this times, yep. So now let's just quickly look how to apply this to this chain. Yep, just quickly think and apply this formula. Damn, it's so small. Yep. So now we have to apply that thing to this circuit. Yep. Yep. So we want to actually convert that thing to equivalent, and the equivalent will be like these ones turn to the R, these ones turn to the R, again, again, and again, again, and we actually end up with something like that. So we get the ground here, and then we go and get the R value to the N3, I guess. Yep, so we get the R here. No, actually one R. Guess that there should remain like one resistor, but or no, like we get the R here, like basically another R. Well, no, there actually should be probably two resistors here. So another one is here in 4. Oh, I probably can't see, by the way. You probably can't see. One moment, guys. I'm just gonna quickly move my camera here, for example. Yep. So here's the N4. And by the way, you probably haven't seen, like I actually managed to prove that formula. Yep. Probably incorrect, a little bit incorrectly, but okay. Actually, it's interesting to find the correct answer there. So here we got the 2R resistor, here we got the B1 bit that is going to V reference. Yep. Basically, what do we got here? We basically have a circuit where there is like the voltage source with VR, and then we get 2R here, what the you might have to sleep more. 2R, and here, well, basically 2R as well, because they are actually sequentially connected, so we can count them up as 2R, and then it locks. Yep. I just adjust it a little bit to have more space. Yep. By the way, quite interesting thing. Okay, so we want to find this V out, or no, or actually this V out. Guess we actually want to find this V out after like dividing all that stuff. So following the formula, we'll have like the V input, and the V input is basically the V reference, and as for the resistors, we'll get the 2R here and 2R here, 2R here, because they are basically equal. So we'll get the 2R here, 2R here, and 2R here. We can actually divide by R because it's non-zero, and get the VR divided by 2. Here we go. If we'd had, if for example there was, let's assume that we had not the third bit equal to 1, but for example the second one equal to 1. How the formula would change? We actually would still have 2 R's here, but we would also have 1 R here. Or actually no, we'll get the that actually would be a little bit more complicated. But actually no, we would get actually 4R. 4R on both sides. No, get the... That's interesting. That's actually interesting. Like these would close up with R. These would close with another R. Oh, so we'll actually eventually end up with 3R. So 1R from here, 1R from here, and 1R remaining. So 3R and 1R again. Yep. So actually, if I'm not mistaken by any means, I don't know, we would get something like that. 3R here, 3R here, then 1R here. Yep. And or no, actually the other way, 3R here and 1R here. Yeah, so we got 1R here and 3R here, and basically that means that V out would actually be equal to V reference multiplied by by R divided by 3R plus 1R, basically VR divided by 4. So yeah, that is actually correct. That is actually correct. So yeah, okay, guess I should end the video right now, because other way, guys, I would mess up the studying seriously. So yeah, good progress. Yeah, it's small, but at least I now barely understand how the 2R, like R-2R DAC works. It's actually pretty cool. And I would like to say like important words, because consistency is actually a key. Yes, I probably do not that much, but I still do it every day, you know, and I hope I will continue to actually make these videos, because even though the progress is not that serious due to my studying, it's better than nothing. It's actually better than nothing. Yep, I know it's probably not that epic as probably this video or this video, probably not, but it's something. And I will just continue to document my progress, and I hope you guys enjoy this. So if you enjoy this, hit the likes, subscribe, leave a comment if you want. and good luck. I hope I motivate you somehow. So yeah, have a wonderful day, guys. Bye. See you tomorrow.